girls. So we're going to do this extra question. It's not on your handout. What I have done is I put it in a Word document up on Schoology, so I want you to have a look at it. I think we need to do 2 examples of these. So a uniform rod AB of length 4 meters and weight 80 newtons is smoothly hinged at A to a horizontal floor. So I have drawn it here. One end of a light inelastic string is attached to B, and the other end of the string is attached to a horizontal ceiling. So this is what we have. It says the string makes an angle of 60 degrees with the ceiling and the rod makes an angle of 30 degrees with the floor. The rod is in equilibrium. Show on a diagram all the forces acting on the rod AB. Okay, so the first thing we're going to do is just draw the diagram with just the rod. The forces acting on the rod. Okay, so it's smoothly hinged here at A. So a hinge acts at that position, so I'm going to draw in the hinge forces there. I'm going to call them X and Y, both going in a positive X, positive Y direction. Weight force, 80 newtons acting down, and of course the tension in the string. That's my first diagram, that's my forces diagram. Second part of the question says, write down the 2 equations that arise from resolving the forces horizontally and vertically. Okay, so the one I have to resolve is this one up here. So I've got my my rod. I have X and Y. I have the weight force acting down. And then I have this T force here. So this is my tension force. So what I'm going to do is draw a right angle around that tension force. This is my tension force here. I'm going to draw a right angle triangle around it, going up and across. Remember this angle here that it makes with the ceiling is 60 degrees. Sorry, this angle there is 60 degrees, which allows me then to label these 2 sides. So this one, because it's opposite the angle, is T sine 60, and this one, of course, is T cos 60, because it's the adjacent to the angle. Now I'm just going to redraw that, because what I want to do is I want to have them both coming from the position where T is, so that when I'm doing my distances it's easier to see. So this is the T sine 60 there, and this T cos 60 I'm going to put it here, just at the base of where the string starts, and that gives me a better idea of where to see the distances up from. Okay, the rod, it says, is it's in equilibrium. If it's in equilibrium, it means that the up and down forces are equal, because that's X and Y. So I'm going to say that my up and up force is T sine 60 plus Y is another up force, is equal to the down force, which is 80. And my left and right forces must be equal. So that means that X is equal to T cos 60. Okay, so these are the 2 equations that arise from resolving the forces. Now I'm going to write down the equation that arises from taking moments about the point A. Okay, so in order to do that, I'm going to have to get a distance diagram. So I'll draw a distance diagram next. So here's my rod. This is my fulcrum here. This is my point. I know that I've got an X force going right through the fulcrum. I have a Y force going right through the fulcrum. The other one I'm interested in is this one here, the weight force. Now look at its distance from the fulcrum. It's from here to there. The length of the rod, it tells me, is 4 meters. So that means if this angle here is 30 degrees, this one here is going to be 2 cos 30, because that's half the length of the rod. So 2 cos 30. The next force I'm interested in is the T sine 60 one. So here's its line of action, T sine 60. There's the distance it is from the fulcrum, from there to there. So that's the entire length of the rod, and again it's the adjacent side, so that's 4 cos 30. The other one I'm interested in is this one, the T cos 60. So here's its line of action. How far is it from the fulcrum? It's from there to there, from the fulcrum, which is the same as from there to there in that triangle. So this is 4 for the length of the rod. That's the opposite side to the angle, so this becomes 4 sine 30. Okay, so they're my distances. I want to get the moments, so I'm going to have to use the anti-clockwise moments equal to the clockwise moments. So I'm going to move that rod about the fulcrum A. So to move the rod is going to, if I move it in an upward direction, that's going to be forces up from the right. And if I'm going to move it in a downward direction, it's going to come down with forces from the left. Okay, so my up forces are T sine 60 is an up force. Y is an up force. From the right is T cos 60. Down is just one down force, that's the weight force, and from the left is X. So that's 1, 2, 3, 4, 5 forces. 1, 2, 3, 4, 5. Okay, the distances now. So to get the moments, I need the distances of each force. So the T sine 60, we've decided it's 4 cos 30 from the fulcrum. The Y, of course, is 0. The T cos 30, is that T cos? Sorry, that should be T cos 60. This one here from the right is T cos 60, and I wrote 30. That should be 60. So T cos 60, that will be, of course, 4 sine 30. That's that one, 4 sine 30. The 80 Newton force is this one, and it's 2 cos 30 away. And of course the X goes right through the fulcrum. So if I write those two sentences now, or if I write that equation, working this fella out, this gives me 4t sine 60 cos 30 plus 4t cos 60 sine 30 is equal to, that's going to be 160 cos 30. Okay, I'll put in the values for all of those angles. So sine 60 is root 3 over 2, cos 30 is root 3 over 2, plus 4t by the cos of 60 is a half, and the sine of 30 is a half, and that's equal to 160 times sine, or cos 30 is root 3 over 2. Okay, so those 2 2s are 4 will cancel with that 4 there. That will give me 3t on this, that for that bit, plus those 2 will cancel with this one here. That will give me a t, and that's equal to, 2 will go into that 80 times 80 root 3. So I have 4t is equal to 80 root 3. So that means t is equal to 20 root 3, and of course that's newtons. Okay, the last part of the question, or I found the tension in the string, the last part says, find the magnitude of the reaction at the hinge. Okay, so again, my hinge reaction is your X and Y forces. So the X and the Y force. If I just move this Y force over here and put it there, I can do that because I can move vectors around once I don't change their size or direction. And this is where I'm starting and that's where I'm finishing. So that's the resultant, that red line there. So to find the resultant, I'm of course going to use Pythagoras. So the resultant is equal to the square root of x squared plus y squared. Okay, so my next thing is to find x and y. So I'll go back up to these equations. X is equal to t cos 60. So x equals t now, which is 20 root 3, by the cos of 60, of course, which is a half. So that gives me 10 root 3. The y force is 80. Bring over that t sine 60. So 80 minus t, which is 20 root 3. And the sine 60, of course, is root 3 over 2. So this becomes 80 minus... that will go in 10 times, 10 3s are 30. So that's 80 minus 30, so that's 50. So that means my resultant is going to be equal to the square root of 10 root 3 squared plus 50 squared. And that will give me, when I work it out, a resultant of 20 root 7 newtons.